Okay. So continuing on then. We had started talking very conceptually about buffers, basically on how they work. Now that we have that idea, I want you to mentally play back what we did up here with the people and the tennis balls, and the tennis balls being hydrogens and then bouncing back and forth. Okay, now we can, with that in mind, go into a bit more detail on exactly what makes a buffer. How do you know if you have a buffer? How do buffers react? So continuing on a little bit more with the conceptual things, just because it's interesting, it gives us that backdrop for why we care, why we're doing this. We talked about how CO2 is an acid, right, when we dissolve it in water. We also talked about how if you have a buffer and let's rephrase, if you want a buffer, you need an acid and its conjugate base. So I mentioned that the way that we control this in our body is through breathing, because we can control how much CO2 we have based on how much we keep in our lungs. In other words, if you're breathing out every little bit of breath that you have, or whether you're holding some in. And so that's one of the ways that we control it. We control how much H2CO3 we have in our body through breathing. And yeah, we don't do this consciously, but our brain's pretty good at it. So as long as you have both of these, it's a buffer. And that's how our breathing works. Again, the biology, any biology here is just FYI. That doesn't mean that I'm not going to ask you about the chemical equations themselves. I can ask you if we add this, what happens to that? If we add this, what happens to this? But the biology is more just a pretty wrapping to put all the chemical things in. So for instance, if you breathe hypo means low, right? So if you breathe really, really slow, you actually don't end up getting rid of all the CO2. You keep more CO2 in your body. And then because of that, more CO2 is acidosis, right? We talked about that last time too. Or if you're hyperventilating. So that's what comes in with like anxiety attacks and things like that. And you end up breathing really, really quickly. And every time you get a little bit of CO2 in your lungs, it's gone. And you might be used to thinking about that as being good, right? We don't want to keep a ton of CO2 in our body. But what we actually need is the right amount. And so we can actually end up with not enough CO2 and actually have our pH be problematic there. So we regulate this through breathing levels. And there's other ways too. We have metabolic ways of doing this, but mostly we can breathe differently. That's cool. I think it's kind of interesting that we can regulate something that complicated through something that simple. Now, why is this bad? Again, this is a pretty wrapping to put around a chemical idea, but it's worthwhile to note. Why do we really care if our blood is off? Well, there's a lot of reasons. I picked one. I picked the one that I think is nice and simple to understand and also interesting. So we have hemoglobin. Quick show of hands for me. Who have heard of hemoglobin somewhere? Okay. Yeah. So we know that this has something to do with red blood cells transporting oxygen. It's important. We die without it. Now, how this actually works is an equilibrium. And I know your book actually talked about this a few chapters earlier in a different idea with embryos and things of that sort. But we have this, and we have this as an equilibrium as well. And it's an equilibrium between oxygen. And if oxygen isn't bound to the hemoglobin, you have acid. You have H+. So this goes back and forth depending on what is going on around it. So going back to Chatelier's principle, which you all did really awesome on, so I know you know. If you increase H+, what happens to this reaction? Does it shift to the products or the reactants? If you add H+, it shifts to the reactants, right? So now the hemoglobin can't have as much oxygen. It doesn't bind to oxygen as well. That's not good. Or what happens if you decrease this a lot? If you decrease this, where does it shift? If you decrease the product, it shifts toward the product. So if we decrease it, now we end up in a situation where it binds oxygen too well, and when it gets to the blood cells, it won't let go of it so that the blood cells can, or when it gets to the muscles or wherever you need it, it won't actually let go of the oxygen. Both is bad, right? We need it to be able to pick up oxygens from the lungs, and we need it to be able to let go of the oxygen when it gets to the places where it's going. And so things like this are all over the place in your body, and if you don't have the right pH, you die. No big deal, right? I'd say life goes on, but it kind of doesn't. this I've said many, many times. I realized I didn't actually really write it down on a slide in big bold letters that it deserved. So here's my slide in big bold letters that it deserves. If you want to have a buffer, you have to have two things. You have to have a conjugate acid-base pair. So maybe that's something that we're used to talking about as an acid, and then as conjugate base. Maybe it's just something that we're used to talking about as a base, and it's conjugate acid, but you have to have that pair. You can't just have any base and any acid together. That being said, we can actually make these using strong acids and bases. So if you happen to see like a strong base or a strong acid in there, don't automatically write it off. We'll talk about that. We can make this situation. But at the end of the day, once everything is reacted, you have to have a strong acid, or excuse me, a weak acid-base pair together. All right? So that's our giant take-home message of what a buffer is and how we get it. Okay. So now let's identify go through and talk about just trying to identify if something is or isn't a buffer. I know I was originally going to do this on there, but I actually just changed my mind. I want to do it on here now, so that I can draw and circle and talk about things. Okay. So we're going to walk through each of these and try to decide. I did rearrange them a little bit, I think, from when I posted it. But we want to walk through this and decide which one of each of these is or isn't a buffer. So we have to decide, do we have a conjugate acid-base pair? Now, in this case, I didn't want to confuse things with a bunch of numbers. So we're just going to assume we have an equal mixture of each, that it's half and half. Okay? Once we start getting into numbers, it does get a little bit more confusing, so we have to pay a little bit of attention. So first, this one. Whenever you look at these, we don't want to pay attention to spectator ions, right? Most of the time when I'm getting questions about, wait, why didn't you pay any attention to this species? Why didn't you pay any attention to this? Where did this go? It's because they're spectator ions. Rule them out right away so we don't have to worry about them. So in this case, what here is our spectator ion? Potassium. How did you know that? Because potassium is like always a spectator ion. Yeah, fair enough. But why is that? It's because it doesn't react with water. It doesn't play a role here. There's no equilibrium that potassium is involved with here. And that's because potassium hydroxide is a strong base. It's not going to pick up a hydroxide, so it doesn't play a role here. So we can just kind of ignore it. So now we have NO2 minus and HNO2. First of all, what is HNO2? What's the name of that? Nitrous acid. Is that a weak acid or a strong acid? A weak acid. And is NO2 minus its conjugate base? Yeah, so is this a buffer? Yes. Okay, now KCl and HCl. We can again ignore spectator ions. So we'll just like scribble out the potassium. It's not going to do anything with water. But wait, we get to chlorine. What do we know about chlorine? Yeah, HCl is a strong acid, so is chlorine going to react with water? Oh, that doesn't really react with water either. Okay, and then what happens when we have HCl in water? What does that do? That completely dissociates. So all of these, I'm going to call it a neutral salt, right? It doesn't react with water. However you want to think about it, you can think of them as both being spectator ions. You can think of them as neither one reacts with water. You can think of their conjugates are both strong, so that's not going to do anything. However you want to think about it. In any case, is this a buffer? No. We do not have a conjugate acid-base pair. Even though it might seem like it because we have chlorine and we have HCl, that chlorine, that Cl minus, isn't going to pick up a hydrogen. It doesn't act like a base. And so that doesn't happen. So we don't have a buffer. Okay, now this one. We can ignore the potassium like normal. Let's kind of scribble that out. So now we have HSO4 minus and H2SO4. We gotta be a little bit careful with this one. It kind of looks like it, right? It looks like we have an acid-base pair. But what do we know about H2SO4? It's strong. So since this is strong, is this a conjugate acid-base pair? No. Okay. The next one down is kind of similar, although there's a little bit of a complication in there. So we can, again, ignore spectator ions. So I'm going to go ahead and just get rid of them, turn them into the proper ion to make up for the fact that I'm getting rid of the spectator ions. I have this. Now, what do we actually generally recognize as like an acid that's associated with this sort of group here? Phosphoric, right? So here, we're actually starting with the deprotonated version. So deprotonated, one less proton. So we're starting with H2PO4. But that still can act as an acid, right? It still has a hydrogen that it can remove to get this. So do we have a conjugate acid-base pair? Do we have something that can act like an acid? Is it weak? Do we have something that is that acid with one less hydrogen? Yeah. So is it a conjugate acid-base pair? Yeah. So it's a buffer. I'm going to do one off to the side. This probably deserves one more example that isn't on here and should be. So let's do another one. Let's do this one. So I wrote that a little small, so I'm going to zoom in. Is that an acid? So we're going to get rid of the spectator ion. I added it just for consistency's sake. Do we have a weak acid? Yeah. It's actually a relatively strong weak acid. It's stronger than a lot of the weak acids, but it's still in our weak acid list. Do we have its conjugate base? What is the conjugate base of H3PO4? What happens if you take away one hydrogen? What does it become? H2PO4. Is this H2PO4? No. Do we have a conjugate acid-base pair? No. This isn't a buffer, actually. So I think that deserves a spot here on our slides. It has to be an actual conjugate acid-base pair. We can't have it just short an extra proton. Okay. Back to our regularly scheduled slides. KCN and HCN. Again, we can ignore our spectator ions. So we'll just not worry about the potassium, which means we have a negative charge here. Do we have a weak acid? Do we have its conjugate base? Do we have a buffer? Yeah. Weak acid conjugate base pair, it's a buffer. Okay, next one. This one is a little bit tricky too. Look at it a second. Make a decision on what you think. Okay, we'll count to 3, right? So we'll go 1, 2, 3, and then you tell me the answer. 1, 2, 3. Okay. That was better than I thought. It was unsure, but still basically the right answer. Okay, so why did I say it was tricky? What do we have to worry about here? H2SO4 is a strong acid, but are we looking at H2SO4 here? No. We're looking at HSO4 and SO4 2-. Both of those, the first proton in H2SO4 is strong. That first one that comes off is. The second one that comes off is still a weak. It's still going to be in equilibrium. So this is a buffer. HSO4 and H2SO4 isn't what we did up here because this is a strong acid. That isn't. That's a weak acid. So that's a buffer. And then our last one. What here is our spectator ion? That one's not quite as obvious as some of the earlier ones. This is, right? Because HNO3 is a strong acid and isn't going to react. So NO3 won't react because HNO3 is a strong acid. So that's actually our spectator here. Now, what is NH3? It's a weak base. And is NH4 plus its conjugate acid? So do we have a buffer? Yes. Now, one thing that you do need to watch out for, and you have some homework problems on, is what happens if we didn't do any reactions here, right? We just said, okay, we have this solution made and mixed up and done. You do have to watch out and see if any of these actually would react with each other. So I'm going to add in one extra example that I think is probably a good thing to do based on what happened in office hours effectively. So that's why it's kind of a last minute add. So we're just going to do it on the back. All right. If I ask you something like this, HCl and NH3. I can't ask you, is that a buffer? Can't do it, because you don't know. And by you don't know, I mean we can't figure it out without some more information, okay? Because if we put an acid and a base in solution together, what's going to happen? They're going to react. A strong acid and a weak base in solution, they're going to react. And so to know if this is a buffer, you have to have a lot of extra information. You have to know exactly how much is in solution and then decide, okay? So what you need to do is, let's say instead I give you some numbers. And I say that you have 0.1 molar HCl mixed with 0.02 molar NH. I'm going to actually reverse that, sorry. I want NH3 to be the bigger one. So I say that we mix, I have to give you numbers. I say that we mix 1.01 molar HCl and 0.1 molar NH3. Now we can do the problem. Now we can see, because now these have to react. They will react until one of the things are zero, okay? If you mix a strong and a weak, and I'm saying that vaguely on purpose because it's a strong acid and a weak base, or a strong base and a weak acid. If you mix those, they're going to react to completion first and then make an equilibrium. So which one here goes to zero? Because it's the lower one. This isn't an ice chart. This is me doing a limiting reagents problem. So if you want to write off to the side limiting reagents problem, that would probably be a good idea. Now we decide if we have a buffer. Do we have a base, or weak base? Do we have a weak base? Yeah. Do we have its conjugate acid? Yeah. Do we have a buffer? Yeah. They're not exactly equal, but that's okay. They're a little off. It's going to be a little bit better at buffering one than the other, but it's all right. Okay? So I added this in because the homework does do this quite a bit, and it is an important idea. Because honestly, in lab, this is what we do a lot. And I don't mean in your guys' labs. I don't mean in labs that are pre-built, you're going in and doing things. I mean, when you're sitting in lab and you're like, I need a buffer, and I only have one bottle, and all it is the conjugate base, what am I going to do? Oh, Well, I'll just start with the conjugate base and dump in some acid until it's the right pH. Okay? So this is the sort of thing that actually we do in research labs a lot when we're just trying to make a buffer that will work with what we need it to. So note that you can do that. I'm going to show you one more with different numbers. Yeah? Yeah, that's the example I'm going to show you right now. Great question. So now what I'm going to show you is the reverse. Now which one goes to 0? You're in H3. Obviously, I'm kind of ignoring the spectator ion. If you want to scribble out the spectator ion, go for it. The reason I'm leaving it as HCl is just kind of as a reminder that we added this into the system, and that's the question that we're asking. So just keep that in mind if you're looking over it. OK, now what do we have in solution? We have a, what would we call HCl? Strong acid, and we have a weak. Is this an acid or a base? An acid. So we have a strong acid and a weak acid in solution together. Is that a buffer? No. Okay. So this is the sort of thing where if I give you a acid-base pair where one of them is strong, I do actually have to tell you the amounts, and you have to figure it out. And it just depends on what you come up with at the end. Okay, so quick review time. So our buffers, the main idea behind them, the main idea why they're useful, the main idea why I declared them for most of you probably the most useful thing that you need to hold on to in this class, is because they keep these large changes in pHs from happening. You add a little tiny bit of a strong acid or base to a solution, it changes the pH dramatically. You add it to a buffer, and it hardly changes the pH at all. So we need this in a lot of different systems. I kind of focused on our blood just because I think it's kind of an interesting thing. But when it comes to actually doing bench chemistry, like we call it on bench chemistry because we're doing it on a bench, it's still really, really important. Because we have a lot of different reactions that we have to run at very particular pHs, and if they don't, they mess up. And you'll get to learn a lot about that next year. So in order to do this, you have to have a conjugate acid-base pair. And they need to be weak, right? Because if you have a strong acid, it doesn't really have a conjugate base per se. So whenever you have this conjugate acid-base pair in solution together at relatively close to equal quantities, so times 10 is fine, but relatively around each other, now you have a buffer. So if you add an acid to it, it's going to react with the, if you add an acid, it reacts with the base or the acid? Base. If you add a base, it's going to react with the acid. That's why you need both. You need something that can actually counteract both the changes from the acid and the changes from the base. Okay. Now let's do some calculations with this. So I know we actually kind of snuck in some simpler calculations, but we should actually talk about how to calculate the pH of buffers because that's pretty important, and differing things off it. The great part about this is we've pretty much already done it. We're going to use the Henderson-Hasselbalch for all of this because these are effectively just common ion effect problems. We know that the Henderson-Hasselbalch equation came from making an ice chart, right? We did that and we walked through it all and we said, okay, we have this ice chart and we're going to make this nice equation that we can use off it. Now, this is just going to be a ton of examples because that's kind of the main way of solving these problems. So we're going to talk about these. I kind of did these for you already in the common ion effect problem. But now that we know that they're buffers, I want to talk about them with you again. I just kind of moved them around. That's all right. Okay, so we already did these. Now we're going to talk about them in a different context is all, okay? So you have these in your notes. Yes? You're looking at me funny. We did these already, yeah? Yeah, we did them in the common ion effect problems. So we didn't talk about them being buffers, though. I instead said, okay, we have this, and we have its common ion. Now, what I want to show you is that all this is this is actually a buffer. Yeah? That what we actually have here is our conjugate acid-base pair, and that it's the exact same calculation. The long dramatic pauses is because a lot of people are still shuffling through, so I want to give you guys time to find it. Okay. The notes might be a little bit different because I think this is my version instead of yours, but it's pretty much the same. Okay. When you do buffer calculations, it is important to note what you are and aren't allowed to do as far as units go. You're filling into the Henderson-Hasselbalch equation. What did we talk about with common ion effect problems when it came to what we were allowed to fill into the Henderson-Hasselbalch? Could we fill in molarity? Yeah. Could we fill in moles? Yeah. Where could we not fill in moles to? Ka, Kb, Kc, Kp, all of those. That's where you start getting into trouble. So buffer problems, whenever you do all of these calculation problems, you're welcome to solve them in terms of moles, and that's fine. Okay, so that's what we did here. I converted into moles. If you wanted to use molarity, you could. Just make sure you adjust for changing volumes. Okay? So M1 V1 equals M2 V2 is how you do that. And if you're saying, I kind of want to do that, just come talk to me and I'll show you how to do it that way too. All right, so we solved for our moles. We solved for our moles here. So now we have our moles of, is this the acid or the base? We're comparing it to this one, right? So is this our acid or our base? It's our base. So that makes this one our acid. Just like when we talked about this the last time, we have to be really, really careful on exactly what we fill in where. Okay? So we have our Henderson-Hasselbalch equation that we made up and that we get to use. And then we get to fill this, the pKa plus the log of the base over the acid. That's why I focus on whether we have a base or an acid. That's also why I picked these two species, right? To remind you of how with these nitrogen-based bases, how you decide what is the acid and what is the base. Well, you have them both here, so the one that's most protonated, the one that has the most protons, is going to be your acid. That goes in your bottom. So we filled that in here. We filled this in here, and we got our answer. Once again, we have to be really, really careful about what we fill into pKa when we're dealing with things that we traditionally know as bases. Because when you go to look up the K for that equation, what are you going to find? K for a base? Kb, right? This, in our kind of chemistry wider world, is what we know as our base. And that's what you're going to find the K for. And you're going to find that that is Kb. And so how do you convert it into Ka? Write this over here, since I didn't explicitly write it out. Ka times Kb equals Kw. So Ka is equal to Kw over Kb. Okay. How are we feeling about the Henderson-Hasselbalch equations? Let me rephrase. Do we want to do the you try together? Because we didn't do that one last time. Okay, that was a resounding thing. On the count of 3, do you want to do the you try together, or can we move on? 1, 2, 3. All right. I seem to have lost that after last time, so we'll rewrite the question. It's all right. Okay, so we're doing almost the exact same thing, right? Here, we have 72 mils of and 20 mils of the other. And you guys are beating me to this one, right? You're going ahead of me, jumping ahead of me, trying to set it up faster than I do. Okay. Now, we need to go through, and we need to say, well, I want to fill into the Henderson-Hasselbalch. This is our goal. If you're still having a lot of problems with kind of general problem-solving techniques, because I know this class is heavy on that, start from the end. So our goal is to fill into this. We have a buffer. We want to fill into the Henderson-Hasselbalch equation. What do I need to do that? I think the easiest way when you're given this much information is to solve for moles. So that's probably what I would do. We need to do it for both. So I'll start by doing it for the base. If you are doing it this way, you need to be careful with your units. You need to make sure that you convert that over. I'll let you in on a secret. If you don't, it will actually happen to work, but that's kind of by a fluke, so you still want to be careful of it. And here we're going to do the same thing. If it's helpful, write the molar out, write moles per liter, so you remember why we're doing this. So now we fill each of these in. Our base into here, our acid into here. This is the same species, so I'm definitely going to just steal the pKa over from the other one. So I'm stealing this from the previous problem. Also, as a side note, I know I mentioned this before, but I'll mention it again. A lot of times if you're working in biology fields, usually you'll talk about things in terms of pKa a lot. Even for bases, you'll generally talk about their pKa more than anything else. And so here we have a pH of 10.2. Okay, next one. The next one I want to do is a little bit different in what I'm asking for. And this is because one of the most important things with buffers is always the ratio between the two. Because that tells you whether something is better at buffering an acid or whether it's buffering a base. It also kind of decides your pH because of that, when you're filling into that log of the ratio. And so it's a useful thing to kind of be able to calculate and know. And sometimes it messes people up because we're not used to using algebra with equations to necessarily solve for ratios. So this is one where we are going to do that. So we're using the blood buffer system again, just because that's what we've been kind of using as our example. And I tell you the pH this time. And I ask you to find the ratio of the two components. All right. You may not right away think you know how to do this. So let's start as if maybe we aren't sure. It's a buffer. Good line of thought as soon as you have a buffer is that you're going to use the what? The Henderson-Hasselbalch. It's kind of your first go-to when you're trying to decide what to do. Now, we want a ratio of an acid and a base, or rather the base to acid. Is there anything in here where we have a ratio of base to acid? Yeah, we have that. That's the thing we're solving for. We're just solving for that whole thing. Okay. Now, whoops, we can fill everything in. We look up our Ka. There's going to be two Kas listed. Do you pick the small one or do you pick the big one? Which one's bigger, the first Ka or the second? First one, right? Because it comes off easier, you're more to the products, Okay, so is this the first hydrogen coming off or the second? It's the first one, right? So are you going to pick the bigger Ka or the lower Ka? The bigger one. Log of A minus over HA. All right. So we end up with 7.4 minus 6.38. This is 6.38. Okay. So we end up with 1.02. How do we get rid of a logarithm? Then to the power of. That's our ratio. So our ratio is about 10 to 1. Now, let's put this in words for the sake of the little question I added in. Is it better at buffering an acid or is it better at buffering a base? So in words, do I have more base or do I have more acid? Yeah, it's a 10 to 1. So I have about 10 times more base than acid. So I have lots of extra base around. Does that mean it's going to be better at buffering an acid or better at buffering a base? What do bases react with? Acids. So if I have lots and lots of base, what is it going to react with? Acids. So what is it better at buffering? Acids. All right, this is another sort of, yeah, hey, we know this, we've talked about this already, but no, really, I think it deserves its own big slide with red lettering. When you start adding acids and bases, don't forget what you already know, okay? Not forgetting what you already know is really an important part to, doing well in school in general and life. But acids react with bases and our bases react with acids, right? So if we add an acid, we're going to turn some of our base into its conjugate acid. If we add some base, we're going to turn some of our acid into its conjugate base. They're going to react. So the next part, and the part that makes what we need to do with buffers, is we want to see what happens when we add acid or bases to the buffer. And to do this, we kind of do it in two steps. The first step is to say this is going to react. Okay? We make what is effectively a limiting reagents problem, and then we do the equilibrium, okay? So you have kind of a two-step process here. See what happens, see how they react, and then after that happens, set up your equilibrium. The nice part is we have the Henderson-Hasselbalch, so at least the equilibrium part of that is pretty okay. So let's go back to we talked about this, but I want to go through it one more time. The way that buffers work is by converting a strong acid into a weak acid, right? Because the strong acid come in, when I had people up here, that was me dropping in hydrogens. It's dropping in hydrogens, and if there wasn't any buffer around, we would just have all those hydrogens forming, or those hydroniums sitting around, changing the pH really dramatically. But instead I had conjugate bases. Those were my people without tennis balls, who came in, picked one up, and said, okay, well, now instead of having these hydroniums, now we just have a weak acid. Sure, that's going to change the pH a little bit too, because there's an equilibrium there, but not as much as if it was just a strong. So what happens is when you take these buffers and you try to add in a strong acid or a strong base, including a stronger acid or a stronger base than whatever system we have, they're going to react. They won't exist in solution together. They will react until something becomes zero. And we had a little bit of a spoiler to that in the kind of add-in question that I did over here, where we did those reactions. So let's take an ammonia and ammonium example. Actually, let's backtrack one sec. If you have NH3 and NH4 in solution together, do you have a buffer? Do you have a base? A weak base? Yeah? Do you have its conjugate acid? Yeah. So yeah, that's going to be an equilibrium, but what I want to show you is the two situations that happen if you are now adding an acid or a base. So if you add an acid, that reacts with the NH3. That's half of the way it works as a buffer. Because if you add a strong acid, there is something that it can do to weaken that. It can say, okay, it's not just going to be H plus anymore. Now it's going to be NH4 plus. It's still an acid, but it's a weak acid, not a strong one. But if we add a base, it's still okay, because we have something in there that it can react with there too. If we have a base, it can react with the NH4 plus, turning into NH3. Okay? Again, if you add an acid, it reacts with the base. If you add a base, it reacts with the acid. So this changes the amounts overall. Notice not an equilibrium arrow. That's important, right? It's going to react all the way. React it to completion, and then once you react it to completion, look at what you have, and then the equilibrium will be set up. So these new calculations, once you react them completely, once you send one of those to zero, that's how you do your equilibrium calculation. That's what you fill into your Henderson-Hasselbalch problem, or equation. Okay, I'm going to skip the steps example because we're just going to talk about them as we do them. That slide's mostly for you guys. All right, so we're going to do two examples where we start adding these in. So our first step is I want you to just calculate, hey, what's a normal buffer before we add anything? Reasons for this are a couple of fold. One, I want you to see exactly how much it actually changes it by. And two, I want to show you something else that comes up quite a bit. And this is a good way to do it. So this is the same as the problems that we already kind of did. We have this. Now, we have 1 liter that's 1 molar. We have 1 liter that's 1 molar of that. We have an acid, a weak acid, and its conjugate base in solution together. What's sodium? Spectator ion. We don't need to deal with it. If you want, you can even just scribble it out and put a little minus sign. That's fine. We fill this in. Now, you can go through the time and effort of calculating the new concentration or the moles, whichever you want, or you can recognize that they're the same. If they're the same, what is going to happen to this ratio? It's going to be 1. And if that's 1, what is the log of 1? 0. So what happens? pH equals pK. That is a good point to know. I know we haven't talked about titrations yet. I also know that some of you guys are stressing out about lab, which even though I don't really do lab with you guys, it's worth noting. This is a special point on your titration curves, right? So if you're in lab, what is that called? It's not your equivalence point. It's your half equivalence point. So if you're not in lab and you're like, why is she doing this to us? Just don't worry about it. We'll talk about it later. It's more just helpful things to kind of point things out that are happening in the rest of your chemistry lives. Okay. So we end up with a pK of 4.74. So it's kind of handy. Now we have that we can use it later on too. Now let's do B. I'm going to do this out in excruciating detail first, and then I'm going to show you the work that you want to do by the time that you are doing the exam on Tuesday. So we are going to add a base. What does the base react with? The acid or the base? It reacts with the acid. So we start by writing the acid. And then it's reacting with the sodium hydroxide. I am going to write this as OH minus. It might not be a bad idea for you to go ahead and write it as NaOH so that you remember that this is the OH minus that is coming from the strong base that we added. Okay? So it's up to you, but you might want to write it like that. Those are going to react until something goes to 0. And I'll put water here for completion, but when you're doing the work, you don't really need to worry about writing it if you don't want to. Now, when you go to do this, my suggestion is to put it in moles. I think that it's faster to do the mole calculation than it is to do the dilution calculation. You can keep it in concentration if you want. It doesn't matter, but you have to make sure to adjust for the fact that sometimes you are changing concentrations. In this case, I wanted to make it simple, and I said that we're not changing concentrations at all, so I don't have to worry about it. So I say that for your homework and for your exam and for your life in labs that you might work in, more so than this problem. But keeping in mind that that is an issue, I'm actually going to stick with doing it in moles. We react it until 1 goes to 0. Which one goes to 0? The OH. You know that because it's the lower one. We get this. Now there is an important step here. It's an important step that a lot of people skip. It's to say, do we still have a buffer? Okay? Because if we don't, we have to do this differently. Don't just start in on this and then say, well, I'm always going to fill into the Henderson-Hasselbalch equation when I'm done. Just because you start with a buffer doesn't mean you end with a buffer. So let's look at this and make sure of it. Do we have a weak acid? Do we have a conjugate base? Do we have a buffer? Okay, so we're good. Yeah? Oh, thank you. Sorry about that. Okay. So we have a buffer. What do? Henderson-Hasselbalch equation. By the way, if you want to write notes to yourself, HH equation is usually the how you prefix it, so it's faster. what number goes on top? The base. That's a nice, safe answer. Which one is that? Yeah, the 1.08. Now, let's make sure this makes sense. Because again, one of the best ways to not make stupid mistakes on an exam is to catch them once you make them, because no one's perfect. So if you go through and you think about this, we added a base. Should our pH have gone up or down? Up. Should it have gone up by a little bit or a lot? A little bit. It's a buffer, right? It's a buffer that we did not, what we call, exceed the buffering capacity. We have a buffer at the end of the situation too. So we look, we compare, sure enough, it went up by a little bit. So we're probably okay. Next one. Going back to the original solution, right? B and C are as if we were going back to the original solution. I don't want to deal with going back and forth, back and forth. Okay. Now we're adding HCl. What is HCl going to react with? It's going to react with the base. So we start by writing the base. Again, I'm going to go ahead and write H+. You may want to go ahead and write HCl. It's up to you. Notice not an equilibrium arrow because I'm saying, okay, it's going to react to completion, and then an equilibrium is going to form. The equilibrium part of this is the Henderson-Hasselbalch equation, right? I could have gone back and did a whole ice chart, but that takes a lot of time, so I didn't. And probably the same reason you're not going to do it. It takes a lot of time. So we just use the HH equation. All right, so we put our numbers down. Be careful on the questions where you're changing concentration, where you're mixing things, to adjust for changing concentration. I'm going to throw in another helpful tidbit for those of you doing the labs right now. That's true of your titrations, right? So be really careful on that. All right, one of these goes to 0. Which one? H+, because it's the low one. And we are back to filling in. Okay, what number goes on top? It's the base, but which one is that one? Yeah. The reason why I kind of stress that one is because they're on opposite sides here and here, right? Because of the equation being the reversed equation. We have that. Okay, I'm going to actually leave this up while we do the review slide, just because a lot of people are still kind of writing, staring, pointing, talking. So we're going to do the review slide just leaving this up. But the idea behind this whole little segment is, okay, we have these buffer problems. We've already set up a system for solving these easily and quickly using the Henderson-Hasselbalch equation. Remember where that came from, though. There's a reason I did that derivation. Not because I'm going to ask you to recreate it, but because I want you to know where it came from. It came from an ice chart, okay? So back a couple of sections ago, we looked at an ice chart that had both a conjugate acid-base pair, and then we walked through and we did the ice chart in a really general format. Now that we have that, we use that for all of our common ion effect and buffer problems, where we can look at this and, well, for acid-base common ion effect. We look at this and we can say, all right, if I have both an acid and a base in solution, I have a buffer. If I have a buffer, I know that small changes, or excuse me, that adding an acid or a base is going to only cause small changes in pH. Again, only if you have that conjugate acid-base pair. Okay, so that's how you decide if you have a buffer. Then if you have it, you use the Henderson-Hasselbalch equation to actually solve the problems. You know, I think I'm actually going to do this one the fast way too. So I know we kind of went on to review and we're going to go back, but I do want to show you something that can speed this up a little bit once you get the hang of it. Because the nice part with buffer equations is you know that you're always going to react an acid with a base or a base with an acid. So if you always want to do this chart, always do this chart. If this makes you feel comfortable and you know what you're doing, do that. I am going to show you one little trick for those of you who get the hang of it pretty quickly and would like to not have to do it every single time. So same problem as this, only faster. We know this. Now, I know how much base I started with. Base over acid, right? I know how much base I started with. I started with how many moles? I started with how many moles? And then I added an acid. If I added H+, if I added H+ to the solution, what did that do to that base? I added acid and it reacted with the base, right? It took some of the base away. Okay? All right. Well, by that same token, I know how much acid I started with. If I had acid and I add acid, what happens to the amount of the acid? It goes up by the exact amount that I added. And you're done. Okay? Notice all we did here is we made this table inside this equation. So I do want to show you that just as a sort of shortcut. It's not really even a shortcut. It's actually just combining work. But do this if you need to, right? Don't do this and like try to come up with all these crazy like, well, if this, then that, and then this other thing in these very specific circumstances. Don't do that. Pay attention to this right here, okay? And then if you're really good at that and you really understand this table, you can save yourself some work by doing that. Okay. So I already started it on this slide. The only thing I needed to add to it was don't forget that technically for all of these buffer problems that we've done, we are assuming the 5% approximation. You don't need to show it to me. You do need to check it yourself just to make sure. If, for whatever reason, the 5% approximation doesn't work, you just have to do an ice chart. Okay? So it's just a little bit more annoying, but you know how to do it. Honestly, it doesn't come up much. That's why I don't make you check it for me. Okay. So this is like a random fun section. It's not necessarily meant to be super serious. I'm not going to test you on the biology here. I mean, honestly, it's more just kind of a, we teach you just enough chemistry to be a little dangerous sometimes in freshman chemistry. And that's actually what a lot of people end up keeping from chemistry, and that's about it. So there's lots of little myths and stuff that comes out. I told you about the lactic acid one, right? Because that one's kind of a cool one that talks about base pairs. So I thought I'd teach you about hangovers today. Because I know that you've probably seen your older friends have them before. And you might be wondering why that is. Also, because of the demographics of this university, I'm going to tell you how Asian flush works too. Because I know your older friends, you've seen it in. Okay. So people who know just enough chemistry to kind of get an idea, and just enough biology to know the pathway of how alcohol works will a lot of times tell you that acetic acid is the reason why you get a hangover, that you have acidosis. And you do actually have acidosis, but not quite in the way they think it is. So this is the pathway. So if you're not familiar with the term pathway, all it means is that, hey, when things go into our systems, our bodies do a whole bunch of different things in a row to break it down. And this is true of alcohol too. This makes you drunk, not you, your friends. This poisons you. This is the thing at the end. And this is often what a lot of people have blamed for the hangover. Because what do we notice here? What is this? It's an acid. Yeah? So since it's an acid, and we have acidosis when me have hangovers, or older people like me, we're videotaping. We've got to be very careful what we say, right? It turns out this isn't actually true, though. So I thought I would show you why. OK. So this is definitely true. This goes through. Acetaldehyde, don't worry about the name or anything like that. It's not an acid, right? It doesn't have this carboxylic acid. It looks close, but it's not quite. You get headaches, vomiting, makes you really sick. This is not what you want in your system really ever, if you can avoid it. This, on the other hand, is pretty harmless. Does anyone know the other name for that? Like if you cook with it or something? Acetic acid? Have you used it in lab? It smells like something. Yeah, it's vinegar. So if just ingesting a little bit of like vinegar and letting that go around hurt us, we would have problems. That would mean that our blood really kind of is not particularly good at buffering an acid or a base. So it turns out this isn't actually a big deal. That's not what causes the acidosis. So like with everything, if I'm going to dispel a myth, I should probably tell you what actually happens. So what actually happens is that when you drink a bunch of ethanol, you end up having, and again, you may know friends who have had this happen, you have to go to the bathroom a lot, right? And what that does is it depletes all your water and it depletes all your electrolytes. And if you don't have any electrolytes, you actually can end up being in metabolic acidosis. You actually mess with the systems in your body, and your body actually puts you into acidosis because of the lack of electrolytes, which is why on Sunday mornings or Saturday mornings, you can walk down to Albertsons and watch everybody hoarding Gatorade. That's the reason for it, is that's why it helps out, is because you're actually just depleting electrolytes completely. Again, this is for fun. This is not testing purposes. Because again, university that we're at, interesting story, what Asian flush actually is, there's two versions of it. There's a protein that does this, and there's a protein that does this, okay? Depending on the situation, there's some genetic mutations that actually causes this to not happen correctly. And again, it kind of depends on the situation, but what happens is this right here slows down, okay? So this is either normal or speeds up. Actually, some people have like a double mutation going on, which makes it even worse, where this builds up. This thing right here builds up. Remember the thing that I said you don't want. It doesn't make you drunk, it makes you sick. This thing builds up because this never happens or is very, very slow. And so it's why there's actually, if you pay a lot of attention to people who are drinking and people who get that particular reaction, they are not quite the same kind of drunk as other people. And that's actually because they're more poisoned than drunk. Because, yeah, I know, sorry. Because this builds up. And so that's why you get the kind of red face and the headaches and the things like that, rather than the normal symptoms of being drunk. It just happens that whether you're drunk or whether you're poisoned, you tend to get headaches and stumble around a lot. And so they look very, very similar. Interesting stories for you. OK. That being said, if I ask you if acetic acid is an acid, that's not because of this slide, right? That's because you know that acetic acid is an acid. So you still have to know like all the random other things I taught you. It's just that little section is kind of more for fun than anything else. OK. So let's talk about titrations. How many of you have done a titration, both either here or somewhere? All right. So we're going to start by kind of doing the experimental setup. I'll probably rush through this a little bit since most of you guys have kind of done it. But we also want to know the reasons for doing a titration. And sometimes that's better done in a place where you're not actually doing it, so you get the idea of the big picture. Why do we care about titrations? Why do we do them? Especially from a historical standpoint, why did we do them? We want to know exactly what's happening, not just how to get the answer. I used to TA a lab a lot when I was when I was in graduate school here, and be really careful when you're doing labs, especially because of the practical, to be really, really aware of what is happening all the time. Don't just go at your lab reports on like how to get the right answer, because it'll hurt you quite a bit. This class is the same way. So be really careful to understand what is happening and then know how to do the problems, okay? For whatever reason, that is an especially bad issue with titrations with people. The focus ends up being on exactly how to get the right answer. You need to understand what's happening first, and then the complex problem solving actually makes a lot of sense. Otherwise, the problems look a little bit overwhelming. So focus first on what's happening, then move on to the problems. And then we'll talk about titration curves and figuring out whether you have an acid or a base and whether your burette would have an acid or a base. So this section is very just kind of introductory. So your general system for this is you have some sort of beaker or flask. Actually, generally we use Erlenmeyers, not beakers, because you can swirl them around easier. But in here, we don't know what this is generally. The idea of a titration is to figure out what is going on in that beaker. And that goes, there's acid-base titrations, which I think is what you did in lab, but there's a lot of other titrations as well. And those other titrations have different reasons, but in all cases, it's figure out what's down here. Now, this large glass thing, it looks kind of like a really, really huge pipette if you haven't seen one of them. But along the sides are all these little what we call graduations. There's measurements. And they're usually like that big, something about that. And the idea with these is that you can measure very accurately exactly how much of something you added. And you can keep adding more. So if you tried to do this with like some sort of pipette, even a really, really accurate one, you would have to continually drop in, drop in, drop in. It would be annoying. So this is just a nice way of being able to say, I know exactly how much of something I added. We know what's in the burette. This is our known. We don't know what's in our analyte. Okay? So we have our titrant and we have our analyte. And we'll know exactly how much we add. We'll calculate that by just looking at the graduations. From what we know about the burette, what we put in the burette and how much we added, we can figure out exactly how much is known in the analyte. That right there is the main goal of the titration. We're going to talk about a lot of other things too. We're going to talk about the half equivalence point. We're going to talk about the buffering regions and past the buffering regions and calculating the pH. We're going to do all of that because it's important. But this is the main idea. The main idea is how much of whatever it is that we're talking about is in here. How much pure is it? Or what's the molar mass of it? Or a variety of other things that we can figure out. But our goal is always figure out what is in here. Okay? Okay, so we have a bunch of different kinds of these. And we can start, and we're just talking about acids and bases in this class. Again, lots of other ones. But let's start with what happens if you have an acidic analyte. You can tell the second you measure the pH whether it's an acidic or a basic analyte, because you know what the pH of an acid or a base is. So if the pH is lower than 7, what do you have? An acid. If the pH is greater than 7, what do you have? Base. Now, depending on what you know about what's in the beaker, because different situations mean different things, maybe you don't even know what it is. Maybe you have no idea what it is. It's actually unknown what the compound itself is. Well, you might get two different situations. In this case, it starts rising up when you start adding base. So this is volume of base added. So you just kind of drip, 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 drip it in. And it just kind of keeps going up until you reach a certain point. We'll discuss this in more detail. And then shoots up, and then it kind of levels off again. Notice the difference here. Here it just continually keeps going up. Here it starts going up, and it's still going up. But what does it kind of do? Levels off. And we call that a buffering region. We'll talk more in detail about it as we go along. But that buffering region is caused by the fact that you have a weak acid-base pair in solution. It's caused by the fact that you have a buffer. This only happens if you have a weak acid down here, okay? If you have a strong acid here, that's never going to happen because you're never going to have a buffer. You're never going to have this region where you're changing a strong base into a weak base. So they look different. You can tell right away what it is just based on whether you get this kind of leveling off or whether it just keeps exponentially going up. Same thing is true of the basic one. You have these two different situations where you can either just start adding in your acid, it goes down, 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 shoots all the way down, and then kind of keeps going. Or you get this little leveling off. When you get this little leveling off, that's what we call your buffering region. Okay, so you get this little buffering region, and then it's, once you hit here, you hit that exceeding buffering capacity. All of your analyte, all of your base is reacted, and it shoots down. Same thing here. Once you hit this point, all of your base is reacted, and it shoots down. Due to the fact that like almost all of you have done a titration, I'm not going to do this because it's going to bore you. Play around with it on your own. If you have not done a titration, we still have some time, but I'm just skipping it so that I don't bore you guys too much. If you have not done a titration, it is absolutely mandatory for you to go do this. Yes, I'm not going to check, but go look at this, play around with it, see what happens. Because the titrations are an especially lab-based thing, and so if you don't have that, you're going to be confused. So because we're actually coming after lab, we're again not quite done yet, so please quiet if you're going to pack up. So the idea with our titrations are always going to be you have this thing that we don't know about in the bottom. We're trying to figure something out about it, maybe percent purity, maybe molecular mass, maybe just if it's strong or weak, maybe we don't really know anything. And then our burette, our titrant, is something that we know everything about, and they're really, really exact. Those are usually bought as standards from a company who knows exactly what is in them. They're very, very accurate, okay? And at that point, we can identify a whole bunch of things that we'll talk about as we go along. And you know what? I think we are actually going to end a couple minutes early. So I am going to post a little podcast on weak acid, weak base titrations. It's not testable. Nothing on titrations is going to be midterm 2 testable, but it's for you to have in case you're having issues with your other class to kind of help out a little bit, since I know we are running a little bit behind